quadratic functions are next level up from linear functions, I guess, in the polynomial function range. So linear functions are degree 1, or technically they could be degree 0. Quadratic functions really do have to be degree 2, i.e. There's an x squared term within the quadratic function. Doesn't have to have an x term, doesn't have to have a constant term, does need to have an x squared term, or t squared, or whatever the independent variable is. The critical points do change a bit. I'm assuming you're already familiar with quadratic functions, so I'll go to the base graph in a second. So you might want to pause and think and write down what you think the critical points are before continuing on. But I'm hoping you would have come up with x-intercepts. They're critical. Commonly called zeros. There's y-intercept, always 1. And they're commonly known as the y-intercept. I can't think of anything else it'd be called. And the third thing is the turning point. That's the critical points. You really do need those. To be honest, if you correctly calculate those 3 things, and you know that a quadratic is a parabola function, you're pretty good to go, because there's no real variation in what a quadratic function looks like other than being fatter or skinnier or upside down. But the other critical piece of information that you would be looking for is to see whether it's concave up or concave down. But I'll explore that in a moment. The forms, f of x or y, you can use either of those things depending on the notation you want to go for. F of x or y is equal to ax squared plus bx plus c. That's called the general form. A cannot equal 0. The other one is f of x is equal to, or y is equal to a outside of x minus h all squared plus k. That's called turning point form. H and k are any values including 0. A can't be equal to 0. So it goes for that as well. The last one's probably worth looking at. Is it's messy to write, but it's something along the lines of, I'll try not to be too complicated. Ax minus b, cx minus d. Don't get caught up with the letters. It just means that they're two factors. So this is called sometimes called intercept form or factor form. Intercept form because we can use the null factor law to work out what x is equal to when that thing is equal, when this whole thing is equal to 0. Now, each of these forms have their own strengths. Really quickly, because I will spell this out in more detail in subsequent videos. The strength of this one here is that you could get the y-intercept straight up. The strength of this one here is that you can get the turning point straight up. The strength of this one here is that you can get the zeros or the x-intercepts straight up. Well, with very little work anyway. You can always go from one form to one of the other forms, except for this one, if there are no x-intercepts. But other than that, you can sort of traverse between forms if you want to. But frequently, it's probably easier to use other methods to try and work stuff out. What do I mean by work stuff out? I mean work out those critical points. Okay. Base graph. I'm just going to do this really roughly because I'm pretty confident most of you, if not all of you, already know this. The base graph, it's an art form drawing under the best of circumstances, to be honest, but the base graph is a parabola shape. It is symmetrical. They're always symmetrical, actually, not just a base graph. It has a turning point at 0, 0. It's symmetrical about the y-axis. In other words, if the y-axis is where I put my mirror, this side would look exactly like this side here. And it's concave up. So what do I mean by the base graph? The base graph is when I've got y, or f of x, equal to x squared. It's the most fundamentally simplest quadratic function you could possibly imagine or could possibly write down. Okay, so f of x is equal to x squared. Looks pretty much like that, but there are plenty of other examples. So I'll do that in the bottom left-hand corner there, slide 7 by this naming. I'll do it in blue just so I can sort of see. Other examples might be like this. Okay, concave up, still symmetrical about the y-axis, but no intercepts. Concave down, and I'll just put it off to the side here as well, just to make it different again. We've now got a y-intercept that's not the turning point. So we've got a y-intercept down here. We've got x-intercepts. We've got concave down. What else could we do? We could do like that. And this is concave up. We've got two x-intercepts. We've got a y-intercept. Turning points down here somewhere. And maybe just one more. I'll give some more love to the left. So, like so. So it doesn't actually, it does have an x-intercept. It's got 1, which is also the turning point. So it bounces off the x-axis. It's concave up. It's got a y-intercept. I should say that the base graph also has a y-intercept as well. Y-intercept at 0, 0 as well, and an x-intercept. So it's all 0, 0, 0. But you can see that these graphs can sort of shift around. And what you can't see here, that I could just spend the next 3 pages doing different examples of quadratic functions, but they're effectively the base graph, which has been moved into different locations, flipped like this one. And what I haven't shown you here is that they can be made skinnier or fatter as well. We call them dilations. But they're all basically the same thing. I might just in red just draw this line in here. And for this graph, it would be, oh, well, I mean for it to be here, but here it is here. Here it is here. You might have come across this already. And if you have, just say it loud and say it proud. The ... is equal to the axis of symmetry. It's an equation of x equals something. So it's not a function, it's just an equation, x equals something, to make it a vertical line. And it's as it says, it's where it's symmetrical, where the parabola is symmetrical. Okay, critical point finding. So you've got just the usual things really. You've got the y-intercept, that x equals 0. So it's the value c if you've got it. The x-intercept is where you let y equals 0. So you've got a whole bunch of properties from last video, from the last unit of algebra, that allowed you to work out what the value of x is when y is equal to 0. So we have the null factor law, for example. So that's from factorizing. We have completing the square. And we have the quadratic formula. So all of those things that you used last unit, you'll need to use again this unit. And it's probably the more complex part of the job is finding those x-intercepts. The y-intercepts are relatively easy. And for the turning point, which you'll find me quite frequently just calling it TP. For the turning point, there's a whole bunch of things that you can do there as well. I'm going to leave differential calculus aside to when we actually cover that. So ignoring that for a start, you've got axis of symmetry. Which is the midpoint of the zeros. You've got turning point form, where h comma k is the turning point. We'll explore this in more detail over the next bunch of videos. And you've also got x is equal to negative b on 2a as being the x coordinate. and then find y coordinate. So you can do that. It's a bit mathematical, the negative b on 2a, but we might spend some time trying to explore why that works. So it kind of depends. So there's a bunch of methods there, and the methods will depend on what you're given. So if it's already, say, for example, in turning point form, there is no c value. And so to work out the y-intercept, you might just substitute x equal to 0 and then just solve it from there, ah squared plus k. If similarly here, you might just substitute x equal to 0 here to find the y-intercept. For the x-intercept, if it's in this form already, you might just substitute let x equal to 0 and then solve. For this one here, you can use the null factor law. For this one here, you might want to use the quadratic formula. Or maybe it is that you want to just translate it from one form to the other and go from there. And again, the turning point, if it's already in turning point form or it's easily done, then you'd be mad not to use turning point form, of course, to give you your turning point. Your axis of symmetry from the midpoints would be good if it was already in intercept or factor form, because it's a relatively easy thing to work out the midpoint between the two values there. That's assuming there is two values. I mean, look at that one. There are no x-intercepts. So how do you work out the axis of symmetry if there's no x-intercepts? But you've also got this negative b on 2a as a surefire way of working out the x coordinate and then substituting that value in for x to work out the y coordinate. So there's a bunch of ways there. So in the next few videos, we're going to have a look at the different kinds of methods you can use to get a graph out of a function. But in the video after this one, I'm just going to go through another example on how to work out the x-intercepts given a function so that you can graph it. That'll do for today's video.